So in this talk, we're going to talk about phosphorylations in specific. Everything I will say is generalizable to many other PTMs. I'm going to be reflecting on some things that we've learned throughout the course, highlighting some things that are a bit different when we're looking at PTMs. Some of them you have already heard along the talks in questions or in slides, and then the purpose of this talk is to kind of wrap everything together and of course highlight some special considerations that are related to phosphorylations and when we do targeted proteomics. So just to recall, because we did it on the first day, when we want to add modifications in Skyline, we go to the tab Modifications, and then we can edit the list of modifications that we want to include. In this case, we wanted to include phosphorylations on ST and on tyrosine, and then we open a menu. There's here a menu of all the other modifications you're interested in. Today we'll focus just on those. And then once we've opened this modification, we can set on which amino acids it is, and quite importantly to set that it's a variable modification. How do we get then modified peptides into Skyline? So there are two ways. One is to import a modified peptide. So you can set Skyline accepts the mass shift or just there's a small label for a modification. When we kind of copy paste our list of peptides, we can include these modifications. Also, if you have a cysteine, don't forget to add the plus 57. If you have a label, you can add the plus 8, etc., etc. So every type of modification that is set in the tab can afterwards be pasted into Skyline. The other option to set modifications is to just set empty peptides and then to modify the sequence. So if we have here a sequence, we can click here on Modify, and then we have a list of isotope modifications, so our heavy labels, a list of structural modifications, and then we can scroll down and choose. And what it will do, it will add this modification and of course adjust all the other parameters accordingly, such as transitions and so on. So these are the two ways of getting modifications inside. The pipeline that we usually use in phosphoproteomics, or so far we've discussed this pipeline that we do protein extractions, we do peptide gestation. Here we want to choose our targeted proteins, whether we're doing targeted acquisition or data-independent acquisition. We would choose prototypic peptides to quantify, and then we go to the mass spec and acquire the data. Quite often in phosphoproteomics, we do fractionation or phosphopeptide enrichment or a combination of both. If you're doing other modifications, you might be working with purified peptides that were used, for example, with immunoaffinity purifications or other things. This talk will not cover about how different ways of doing this step. We're going to focus on the mass spec data, on the targeted proteomics aspect of it, not about how you prepare the phosphosample. What is going to be extremely relevant, and we're going to look a little bit more into detail here, is how we use LC retention time, and to some extent how we use relative transition intensities, because these become extremely relevant when we're looking at PTMs. We've also seen at the beginning of the week that we go through a process of selecting proteins, and then we select peptides, and we gave you a list of recommendations how to select the best flying peptides per protein, how to select these unique peptides to have maximum selectivity. We gave you a list of tips to achieve those prototypic peptides and from those quantitative peptides, so we can quantify the proteins of interest no matter what type of acquisition we're doing. These, of course, don't apply when we're doing phosphoproteomics. Usually we're kind of stuck with a list of phosphopeptides. They don't always apply to any of the criteria that we had, but we do recommend you to be aware of these. So if you're looking at a miscleaved peptide, whether it's a phosphopeptide or not a phosphopeptide, it's always good to keep in mind that this is a miscleaved peptide, and you don't know if this miscleavage is reproducible or not. So if you're looking at a very short or very long peptide, again, if it's a phosphopeptide, it doesn't actually matter for that for that particular case. We should be aware of this situation, but with phosphopeptides, quite often we don't have the choice, and we take the phosphopeptides that we're interested in and just follow them up, and we don't choose prototypic or quantitative peptides, but we choose differently. What I always recommend to people is if you're going to work on phosphopeptides and targeted proteomics, there's quite a lot of information out there in different databases. Here I just listed the three that I use the most often. And you can access this data very freely and find out what is already known about the phosphopeptides you're gonna be examining. You can find out when were they measured in the past, how much is known about them, how much is known about the biology behind them, and so on. And acquiring this information before you start your targeted proteomic experiment could be quite useful in selecting the phosphopeptides you want to work on. And one of the big problems that we have with phosphopeptides, but for that matter with any type of PTM, is that when we're looking at regular peptides, we go from the MSMS spectra and you go into peptide identification. And when you look at modified peptides, in this case phosphopeptides, the other issue that we deal with is the localization or the assignment of the site of modification. So first we need to identify a phosphopeptide, and the second step that we need to do is to assign a site where is the modification occurring along the peptide. So quite often when we do phosphopeptides, we start from a global phosphopeptide experiment. We do a shotgun discovery type of experiments, and this has been an ideal and has been extensively developed to do global identification and quantification of the proteins, of the PTMs, and so on. We come out with a very, very big list. And what you've probably noticed is that if you've done phosphoproteomics, is you come up with a list. This list is associated with a list of probability of identifications, and in recent years, maybe with a list of probability of a probability to assign the phosphorylation site. So we have two types of probabilities. One is how confident I am that I identified the right phosphopeptide, and two, how confident I am that I assigned the site in the correct space. But at the end, we get a list, and there's all of these options. And of course, don't forget that if you're going to work with Skyline and you're going to import this file, as we've done in one of the tutorials, all of these, if they pass the cutoff of the probability of identification, will all go into Skyline. So we'll have one library with a lot of different site assignments. The other problem that comes is not just a very long list, but when we look at the quantitative data, so when we start to look at where are these, when we do, for example, LFQ, then we quite often get these types of missing values. This is just figuratively drawing a quantitative table where we would have different site assignments, and then sometimes we get a value, sometimes we don't get a value, sometimes we get a value, sometimes we don't get a value, sometimes it looks kind of complementary, and we're not sure what's going on. Are these real missing values? Is this a problem with the alignment? Are these different phosphopeptides? What's the deal? And one of the things that can certainly happen is that when we have, this is a figurative LCMS peak, we had shotgun at the beginning of the peak, and then we identified one phosphosite. We had another shotgun event at the end of the peak, and we assigned a different phosphosite. These assignments happened during the search, not during the acquisition, of course. And then some of the time we're quantifying this peak as belonging to this site assignment, some of the time we're quantifying this peak as belonging to this site assignment. So we have two phosphosite IDs in shotgun, one LC peak, and we're not really sure, are we having false site assignment or not? How do we deal with these? Should we merge them? Should we consider them as separate identities? We're not exactly sure what to do. And that's where targeted proteomics comes in. In targeted proteomics, we can try and account for these differences and try to very accurately do PTM quantification and to control for the correct site assignment. So we're going to go through some different tools that we use in targeted proteomics to kind of always keep a handle on these parameters. So far, we've looked at these types of tables and looked at different parameters, and we've always looked at the level of the protein, at the level of the peptide, and so on. And of course, now we're going to expand this a little bit more, because for one peptide, we could have several possible modifications. So if before we were looking for transitions to gain sensitivity and transitions that uniquely describe the peptide to gain selectivity, now we need another set of transitions, and that's the transitions that will describe selectively the phosphorylation site. So there are two sets of transitions. One are for the identification of the peptide, and a second set of transitions is for the identification of the correct phosphorylation site. And let's take an example. So this is a yeast protein. We have these different peptides. three different assignments. We're going to call them phosphopeptide isomers, and these are these cases where the amino acid is the same. There is one modification, but the localization of the modification is different. And these would be the phosphopeptide isomers. And then we're going to do transition selection. So we saw how did you do it this year, in the beginning of the course and of this year. So we selected B and Y ions, and we selected from a certain mass range, and then we get these three lists. So what can look at the lists, and what do you see, or what's the difference, or do you spot anything special about the lists? Correct. So makes sense, right? If this phosphorylation site is here, here, or here, certain ions will have a different mass. We will have those fragment ions that are unique to only one, and you see they occur only when the localization is here, but they don't occur on any of these localizations. Another case would be here. These ions are unique to this localization, but not to others. And then we would have another type of ions that maybe are common to 2 out of 3 or to 3 out of 4 and so on. So if you look, for example, at this B3, it is common to these two localizations, but we don't see it here. Here B3 has a different mass. And of course there's a bigger list here. I just highlighted 2. We use these types of ions, and we call them site-determining ions, as unique ions that enable us correct phosphosite assignment. So if we would be measuring a pair of this precursor and the combination of these two ions, we could be fairly confident, assuming that we are confident that this is the right identification from a site localization point of view, we would be confident that this is the correct site. And the same goes for this localization. So if we have a site assignment here and we measure the combination of these ions, we would say, well, since these ions occur only on this site localization, we can exclude these two localizations and say we're quite confident that this is the right one. What do we do with this one? I mean, now we don't have any type of ion to look at this. Anybody has an idea? Well, I have an idea. The idea is to look at unique ion signatures. We don't look at signal ions, but we look at combinations of ions that are unique. So look at these two ions. They are common to these, but they are not common to this. And this B3 ion is common to these two, but not here. So the combination of these three ions is unique to one localization. So sometimes we can use site-determining ions. So that would be, let's say, 1, 2, or 3 ions that are unique. Sometimes we don't have a site-determining ion, but we have a combination of ions that is unique to one site assignment. So we kind of need to look through these aspects, through these transition lists, and find what is the correct ion or combination of ions that enables us correct site assignment. But it's, yes.
Sorry, but this all assumes the retention of the phosphosite on the fragment, right? Which is...
You mean that we can actually detect it? Yeah. Yes. So of course, this is a theoretical table, and we assume that we can actually see each one of these things. If, for example, we couldn't see B3, then we would not be able to do a correct site assignment for this phosphopeptide isomer, correct? And that's coming up next, yes. So what we have in phosphopeptides and some other modifications is neutral losses. So neutral losses is the process in which we lose the phosphorylation during fragmentation. And then this is something that we can set up in Skyline. So we would set here the number of neutral losses we want to enable. We would set here the chemical formula of neutral losses. And in theory, a neutral loss, as was just pointed out, an ion in this case that lost the phosphor group is also a type of ion that can occur. And actually, if we would enable all of these parameters, we would also see it on the list. So you can see here that you have Y11 and Y11 minus the neutral loss, minus 98. So all of these are enabled in Skyline, and you can choose them. And sometimes, this is, for example, an HCD spectra, sometimes these neutral losses are fairly high peaks in the spectra. So if you would look here, I think if we would choose, for example, top 5, we would choose 3 neutral loss ions out of the top 5 ions. So quite commonly, if we would just go to the spectra, click choose top 5 from the library and not look at the spectra, then we would choose a lot of neutral losses. And we encourage you to do this very carefully. And the reason is the following. So if we have a neutral loss, we had, for example, a phosphoserine, we lost 98, and then we get dihydroalanine. What can also quite commonly happen with CID is that we lose a water molecule. So if we have serine, we lose a molecule, we come up to the same dihydroalanine. And that has implications when we look at phosphosite assignment. So if we had this phosphopeptide and we chose Y7, Y7 would look like this, and these would be the set of transitions with a neutral loss. And if the localization of the site was somewhere else, let's say it was here, Y7 would now not carry a phosphor group, but it can lose a water molecule. And in this case, the set of transitions would be the same. So we would be extracting this set of masses. We think this is due to a neutral loss. It's actually due to a water loss. And so neutral losses or water losses are one thing that we always need to consider when we choose neutral loss peptides neutral loss fragment ions for site assignment. We can, and we sometimes do, use them for quantification, since they are very high abundant ions sometimes, depending on the sequence and so on, fragmentation method, etc. Then sometimes they are very useful for quantification, but they are not useful for site assignment. So whenever you're going to do phosphopeptide site assignment, do not use these neutral loss fragments, but once you have a correct site assignment, let's say with the combinations of these ions, you can then include them in your method if you think they are very abundant ions, and they are sometimes, for the purposes of the quantification. But you need to get first the assignment correct. So now we go to the measurements. We've selected a phosphopeptide, we've selected transitions, and we go to the measurements. And the moment that we move into measurements, we told you the first thing we start to think about when targeted proteomics is the retention time of a peptide, and we said that this would depend on the peptide properties, the sample background, the chromatography, etc., etc. And retention time is going to be an extremely useful parameter here. One of the things is that when we look at peptide properties, if we look at the two peptides we looked before, they have the same mass, but there is something a little bit different in the chemistry of the peptide. The phospho is somewhere a little bit different. Maybe the distribution of charges is a little bit different, the ion cloud, etc. So there is the possibility that these peptides are not exactly the same, and we could separate them. Now, separating them relies on chromatography, so we need to have enough peak resolution in chromatography not to have two different phosphopeptide isomers coeluting in one peak if we have good chromatography, but separated into two peaks. So the idea is to use retention time information to pinpoint phosphosites. And how it works is, theoretically, if we would have some figurative phosphopeptides that has 3 possible localizations, and each one of them will elute in a peak, but if we would try and look at how they elute in respect to each other, one option is that they would be separable in retention time, so that there is going to be a certain sequence in retention time that this, for example, elutes before this, which elutes before this, or maybe these two co-elute or not, we don't know. But to some extent, with good chromatography, maybe you can separate different peptides with different site assignments simply because they have somewhat different properties. This, of course, doesn't always work. We can also have the case where all of these would be co-eluting. They would look very nicely when they are separated, maybe have different relative intensities, but when we mix them together, we don't see any separation. So this is kind of a concept. I'm going to give you some examples to explain how it actually looks like. So we took the peptide that we were looking at before. Remember, we made transitions, and in this case, these measurements were done by Tina. We first measure each one of these peptides separately, and you see very nice peak groups with a very nice ion series. You see also that there's some difference in the relative intensities, and if you note correctly, there's also small differences in the retention time. And when we mix them together, we see that each localization is somewhat separated in retention time. So we can assign to each peak a specific localization. You will also note that it doesn't go exactly by the sequence along the peptide. So 70 elutes after 72 and before 75. So it doesn't work sequentially in any way, but there is a certain order between them, and this order is always preserved. In this type of chromatography, every time that we would inject a mixture of these three peptides, this would be the sequence of the peptides, and if we have good enough chromatography, we will get three different peaks that we can separate, and that allows us to measure three different phosphosite assignments and do them separately. So in this case, we have all the phosphopeptides isomers that are separable in retention time, and then when we go to the real experiment, we of course have now an endogenous. This is a yeast that was grown in some conditions, and the synthetic heavy. These are these synthetic heavies, and then we see that in fact, when we had the shotgun data, one of the localizations was actually wrong. We don't have any light signal here. We only have two heavies. We now need to select very carefully the peak boundaries. So we select the peak boundaries here and here for the light and the heavy. We select the peak boundaries here and here for the light and the heavy. And we basically quantify this phosphopeptide isomer separately from this phosphopeptide isomer. So by considering retention time as well, in this case we were able to separate on the chromatography the different phosphopeptide isomers and quantify each of them correctly. We can of course then do follow-up studies on each one of these site localizations, and that was actually done. This data was also verified with point mutations and so on. So we were fairly confident with the results. Now let's take a different example, which is a bit more complicated. Here we have 5 possible assignments. Again, we measured each one of them separately as a synthetic phosphopeptide, and unfortunately when we mixed them, what we got was something like this. So this is kind of a mess. We have here some peptides that are completely coeluting, somehow separable, sort of big shoulders, etc., etc. I would say that here we would say that the phosphopeptide isomers are not very well separable by retention time. And the other thing that I would like to point out is, before when we were doing tutorials, we called this, for example, an interference. We said we should remove this interference because this is probably coming from some other analyte that we were not interested in. In this case, the other analyte we're interested in could be very interesting. It could be the same phosphopeptide with a different localization. So when we look at phosphopeptides, for example, we should always be very careful before we are removing what we think are interferences, because they could potentially be very interesting interferences for us. What could we do in this case? Any suggestions? Yes? Correct. So one point that we could do is reconsider the chromatography. So this is a case where we don't have enough peak resolution in this time. You also see that it's fairly early. Maybe if we would change the gradient, change the beads, anything like this, we could try and improve the chromatography and get them separated. What else could we do? These were giving measurements. We ran out of sample. Look at the height inside of it. The height of what? Look at the height. Yes? In this case, we cannot exactly look at the height of the peaks because they are synthetic peptides that come from different things, and we don't have a reason to assume that they would have the same. We have no tools to assume that they would have the same heights. Yes? Specific transitions, correct. So what we can do now is, let's take for example these two that are completely inseparable. We don't know 24 and 25. If we cannot separate them by chromatography, maybe we can look at specific transitions. And in this case, I made the table in the form of an Excel table just to make it look easier. But if we look at 24 and 25, which are not separable, by by the retention time, they are separable by transitions. So we would expect for 24, we would expect a Y5 with this mass, and for 25 we would expect a Y5 with a different mass. And indeed, when we look again just at Y5, for serine 22, 23, and 24, we extract this Y5, and when we look at the mix, we have this complex mixture, and for when we look at the mass of this Y5, we get a peak only on these two, and then we get a different pattern. So in this case, we have only one transition that's going to be useful to pinpoint the localization. Of course, it's still going to be very difficult to do the quantification because we would need to set the boundaries here very, very carefully. We have, in theory, only one transition that we can use here. The rest of the transitions might be in common, so we're not sure which one goes where. But at least we can always go back to this idea of site-determining ions or the unique ion signatures and try to look where does the combination occur. So let's take another example. We ordered here a reference peptide. This is the sequence of the peptide that we ordered. These are the transitions that we used. And then we went and measured this in heavy and light form, and we got this phenomena. What would you say happened here? Yes? The naked peptide is not, the endogenous peptide is not phosphorylated. Okay? Any other suggestions? You think, so you say here there's a different background. Okay, but this was spiked in the same background. So these were separated. I showed you how to do this split window. So they come from the same measurement. Yes? Correct, or probably correct, I would say. What can happen is that I ordered here a reference peptide because I looked at shotgun data. I thought this is the correct site assignment. But in fact, when I go to the endogenous, the site assignment was wrong. And now we get a peak that is eluting at a different time. Another option that you should consider is maybe there is some modification that is very, very small, which creates a shift in retention time. That can also always happen. But in this case, we have a heavy that is eluting here, but nothing is eluting at the same time, co-eluting in the light. We do have a very nice P group with different relative intensities eluting at a different time. And if we believe that different phosphopeptide isomers are separable by retention time, and at least most of the time it works, then this is probably simply a different phosphopeptide isomer that we didn't expect. What would we do to look at this? Any ideas? Or which transitions should we look at? Or so just, yes? So yes, we could look at a B series. In this case, I looked at the Y series. And for example, here I just show you Y4 and Y5. Y5 and Y4 on the heavy co-elute very nicely. On the light, we only have Y5. We don't have really a signal for Y4, and of course we have nothing in the expected retention time. So where would you guess is the phosphorylation? Correct, on the Y4. So what we see here is the Y5. This we see in both groups. The Y5 would include the phosphorylation whether it's on this serine or on the next one. But the Y4, we only see it on the heavy. This would be, in the case of the heavy, without a phosphorylation. In the case of the light, we would expect here to have a peak with a phosphorylation, so with a different mass. And I don't have the slide with me, but we validated this case, and then we reordered another reference peptide and got the localization correct. But you see here how we can use both retention time and specific, or play around with these determining ions to try and pinpoint localizations. So, yeah. So to summarize this part, we can look at site determining and unique ion signatures to enable correct phosphosite assignment, and then we can also use accurate retention time information to separate phosphopeptide isomers, and the combination of these two pieces of information are very, very useful when we do the identification and quantification in targeted proteomics. And some considerations when we go and do these types of analysis. First of all, we should consider how we very carefully what we have defined as peak boundaries, so what we have defined as things that we should remove. Before, what we were calling as interferences now might pinpoint to a different phosphopeptide isomer, and what and if we before just selected the top 5 or the top 10, in this case it might also include neutral losses, and these might not be very useful when we want to do phosphosite assignment. If we do have accurate IRT and we do have unique transitions, then we can do the quantification of phosphopeptides isomers. And as I've showed you here, one example, if we have a synthetic reference peptide, then sometimes it's very useful to find these very small shifts in retention time. Because if we look at the example before, if we hadn't had this peptide and we would just see here a P group, we would need to, of course, use all the other scores, dot product, and everything else that we learned along the time. But we could, for example, it might be very difficult to say whether a shift between 12.9 and 13.8, that's less than a minute, is this a very big shift in retention time? Are we in any way sure? So having here a reference peptide was really what enabled us to say at the endogenous level there is nothing phosphorylated on this residue, but there is a phosphorylation on another residue. So although here I've presented so far data when we had the reference, and I gave you some examples to exemplify how we use site determining ions and retention time, in many times we don't have references. If we work with shotgun data and that's our reference for an assay development, then as we've mentioned before, everything will go into the library. If we want to do data independent acquisition, for example, and go to extract these assays, then of course we don't have a synthetic peptide for every phosphopeptide that we ordered. Or it would be nice if we could, but it would be quite expensive as an experiment and maybe complicated to perform. And if we would now have a list of assays with different localizations or combination of localizations, all of them, because we do a probability cutoff, all of them will go in. Maybe we could also do a site assignment cutoff to filter some of them out. But at the end of the day, we will have one big library with various site assignments. And then if we do targeted extractions from this data independent acquisition type of data, then what would actually happen is that we would validate the different assays that they come from our original library, and we would be kind of sort of back in this shotgun situation. We would have a lot of different assays, we would try to extract them, and we would just get a mess. So any type of false site assignments that we have in our library would propagate forward when we do a SWATH or any type of other targeted extraction. So I would like to exemplify this or stress this point in a couple of figurative examples, as we've seen before. If there was an LCMS peak and we had in shotgun only one identification, so we had one site ID in shotgun, one peak, this would be fine for the identification, it would be fine for the MS1 quantification, and would be fine also when we generated a library out of it and went into a SWATH data set. Then we would extract the relative intensities, we would get one peak, and that's completely fine. That's the good case. But if we go back to the example we had in shotgun before, we have one peak. This peak was identified twice with two different assignments, so we have two different site IDs, one LC peak. When we want to do the peptide identification already in the shotgun, we are not exactly sure which one is the right one. When you do the MS1 quantification, as we've seen before, we're going to get a table with a lot of missing values, because sometimes across runs this peak would be assigned to this localization, and sometimes across run this peak would be assigned to this localization. And of course, when we're going to generate a library out of this data, we're going to have two different assays, and this will just inflate the size of the library unnecessarily. So here we cannot know, is this a full site assignment or are these two co-eluting phosphopeptide isomers? We're not exactly sure. If we go to SWATH, we can, if we are not careful, we're going to have several wrong identifications that will be confirmed in SWATH. We will simply try to extract this peak twice, once with an assay originating from this peptide, once with an assay originating with this peptide. But in SWATH, we can at least try to address this issue by try to clarify these identifications if, for example, we would try to build the assays correctly to account, for example, for site-determining ions. And what I've shown you before, we have more of a handle over it than we do on when we're doing MS1 quantification and shotgun type of pipelines. Then we have another example. Sometimes we would have two peaks, and for any reason in shotgun we have just one identification that was assigned to these two LC peaks, of course, or maybe not of course, but we would presume that the peptide identification in one of them is wrong. Maybe there was another phosphopeptide isomer that was actually eluting here. The MS1 quantification would also be wrong. Sometimes we would be quantifying this peak and sometimes we would be quantifying this peak. And when we're doing library generation, we will also have a problem, because what would happen is we would generate a library that sometimes has this retention time, generate a library that sometimes has this retention time. We would average these retention times, and actually we get an assay in the middle that doesn't match any of them. So we have a wrong assay for two peaks and we don't know what's going on. Of course, in the background truth, we don't really know if this is a false peak assignment, this is a chromatography issue, maybe there was a problem here for any reason, or when we go to SWATH, we also don't know, there's another possibility that this is simply another PTM that we didn't consider. If it falls in the same window, as you've seen in previous talks, what we can always do is by mistake have, or not by mistake, by not paying attention, we could have a set of transitions that we use to extract, and they are common to two types of modified peptides. They fall in the same window, and then we extract two peaks that actually at an MS1 level would have different masses. And this is why we can is very useful to do also the MS1 scans. So if we move from this situation into a SWATH-MS, we would have one assay that has a mix from two peaks. We would have the wrong fragment intensities, wrong retention time, and this is the part where we really try to be very careful in SWATH-MS and construct a different assay for each peak. So basically, conceptually, I will explain to you how we do this. I will not go into details. We take a phosphopeptide sequence, we account for the number of phosphogroups on this phosphopeptide, and then we build a separate assay for each peak group. We keep them always separate along the whole pipeline from the first step of library generation till the targeted extraction, and then we are sure that we are quantifying each time a separate peak group. Of course, here we have the problem that we only have information that these two are separated in retention time. We're still not sure about site assignment. So what can we do now? Synthetic peptides would be one option, to order synthetic peptides and get an idea which is which. So the first thing we could do is just quantify in all the conditions and at least be sure that we're always quantifying the correct peak. Maybe we don't know what's the site assignment, but at least we are sure that our table is consistently filled, and that when we're quantifying this peak group, we're comparing always to this peak group and never to this peak group, and so on. And the second thing that we can do in SWATH is try to extract site-determining ions. So we can go back to this concept, and as before, I've shown you this concept in SRM, so we choose these in advance, or in PRM we would look for them afterwards. But in the nice thing about data-independent acquisition is we first measure everything, and then we can always try and extract more ions. So we could go into the sequence of the peptide, try to figure out which are these site-determining ions that I've shown you as examples, and then try and extract them again. And this would give us these unique ion signatures that will allow us to pinpoint phosphosite assignment. So here we basically separate. We can first do assays for quantification that just really ensure that we're quantifying each peak group separately, and then at a second step, a second iteration, we can go and look for these site determining ions, re-extract them to gain confidence in the localization of the phosphosite. And of course, we can always look into the MS1 data to try and understand, is this another PTM occurring on the same peptide, as we've seen examples before with oxidation, for example, or is this really the same mass but two different phosphopeptide isomers, for example? Are there any questions about this part? Yes?
Have series of serine or a mix of serine and threonine. Do sorry. Yeah. Do we have actually some software where we can design different combination of a peptide we identified first to?
So you're asking about the case of multiple phosphorylations?
Yeah.
So, of course, everything that I've exemplified so far is with the case of one phosphorylation that is moving, let's say, along the sequence peptide. Of course, if we would have 2 or 3 phosphorylations, it would only increase the combinatorics of all the possible things. At the moment, I'm not aware of a software that does that. In theory, as you've seen in Skyline, you can do everything related to this in Skyline, so you can figure out, you can extract all the series, for example, the Y-ion series, and figure out which ones are the ones that are relevant. At the moment, what I do is I do it manually in Skyline. I'm not aware of a software that is publicly available. In that case, I would like to summarize. So during this talk, as I've said at the beginning, I wanted to go with you over a few principles that we apply when you do PTM analysis in targeted proteomics. I use phosphorylation as an example because this is what I work on. And I've explained to you the importance of pinpointing the specific phosphorylation sites. So here we try to quantify with high confidence each site separately, and this we do with site determining ions and using the retention time information, and the combination of these two pieces of information allows extra orthogonal information to refine this correct site assignment and ensure good quantification. When we move to large-scale quantitative analysis, we should be very, very careful when we do targeted extraction of data, independent acquisition type of data sets, because then we need to pay extra attention already when we're doing the library. If we are not careful when we do the library, all of these potential errors will propagate into the library and then into the data extractions. We will not be able to spot them unless we, of course, check each peak and each spectra separately. With that, I would like to conclude, and of course, if there are more questions, I'm happy to answer. Questions?